the adsorption. But let's consider the simplest situation. It's irreversible in nature, and the object cannot object will be there forever. Object will be there at the position of adsorption forever. So what is the statement? I can explain. I can elaborate it in more details. Like here we have a lattice in one dimensional lattice. The spaces, the initially it is completely vacant, and one by one the dimers arrive. The dimers arrive, and then they try to occupy the lattice sites. And in the deposition attempt is successful when there is the two neighboring lattice sites are vacant. Otherwise it's unsuccessful. Like in this special case, like this dimer is arriving and is trying to occupy these two lattice sites, and since these two lattice sites are completely vacant, so the dimer will be situated, will be colliding with this particular previously at some instant of time. So that case, so the adsorption is unsuccessful, and then what we do, we again try to deposit the dimer at any other random places. So this way the dynamics continues, and it stops when we get back a situation, we arrive at a situation when the system is in the jammed state. That means there exists no more additional adsorption of dimer is possible. So there will be some vacancies, but those vacancies are singles. All those vacancies are single site vacancies, and in this case, what is the quantity of interest is the surface coverage, which is called the jamming density. But in general, when you deposit dimers one by one, one by one, one by one, so what is the surface coverage at any particular instant of time? So time means the one successful adsorption, one deposition attempt is called 1 unit of time. So when we have in particles in objects which have been successfully adsorbed onto the lattice, so the fraction of lattice sites which are covered, which are occupied by the dimers, is called the surface coverage. So in this case is after adsorbing in objects n dimers, so dimer occupying two neighboring lattice sites, so 2n number of lattice sites are occupied, and the system size is L. So we have L square, let's say in two dimension is in one dimension it's L, so it should be 2n by L. But I will be talking about that I will be showing the results in two dimensions. So it's like L square, so the fraction of the lattice sites, nothing else. And and in this way, when the system is in the jammed state, that means its t tends to infinity, that particular surface coverage is called the jamming coverage, and is denoted here by Pj. So now we will be but other than this lattice, the problem can be generalized in the continuum space. And in continuum space, this problem is well known as the Rayni's-Karpukhin problem, which way back in 1959, the Rayleigh solved this problem in its irreversible limit. As I mentioned, irreversible limit means that there is no question of desorption, there is no question of diffusion. When the object will occupy a place, the object will be there forever. So in this limit, the Rainy obtained a jamming coverage which is 0.74 in one-dimensional continuum space. And in this case, if we ask the same question, how does the jamming, the system approaches to its jamming coverage, and it approaches as a power law fashion. So in this case, it's a power law in continuum space, but in discrete space, it's exponential in time. So as you can see, so in case of a continuum version of the problem, the approach towards the jamming coverage is slowed down compared to this discrete space. Okay, so this is the problem in one dimension, but the problem, let's talk about the situation in case of a two-dimensional system. Let's consider the dimer deposition. The simplest case is the dimer deposition on a 2D lattice. So we have here one extra degrees of freedom, that is the orientation of the objects. So we have two possible orientations. One is horizontal. It's painted in red, and the another one is vertical. As you can see, the objects are painted in different colors. Two different orientations are painted in different colors. Two different colors. So this is the particular situation when the system is in the jammed state, and in this case, these white spaces are the single site vacancies. So, and in this case, what we do, so if we elaborate the statement of this problem, is that we start with a completely empty lattice, two-dimensional square lattice, and then we select a particular orientation of the depositing dimer, which would be like either horizontal or vertical, and they are equiprobable, so they are selected with probability half. And then once the orientation of the deposited dimer is selected, then we try to make an attempt to be at whether it will be a successful adsorption or not. So the restriction is same. There should not be any overlap between the objects. So there exists only one interaction, which is excluded volume interaction. So in this particular case, the problem is not solvable analytically, and the values are known up to numerical accuracies on two-dimensional square lattice. And if it is a the dimer, in case of dimer case, the jamming density is 0.9068. So the more general situation could be the problem of anisotropic random sequential adsorption. In that case, one particular orientation is preferred over the other. Other means let's say the horizontal is more probable than vertical. So we can construct a anisotropy parameter, and we can tune the value, and then we can see what would be the jamming density and so on. So this anisotropy parameter could be varied between one half to one. So half means equiprobable. So we get back the situation of this problem. So the jamming density should be 0.9068. And in case of in the another extreme limit, when it is unity, that means only one particular orientation is possible, either it is horizontal or vertical. So in that case, so it's like a one-dimensional problem. The problem reduces to the one dimensional because we have only one possible orientation possible in the system. So it's a one-dimensional problem, and we get back the jamming density, which is on a lattice 0.86, close to 0.86. So by tuning these two parameter, this anisotropic parameter, we can tune continuously the jamming densities, jamming density between this to this. Okay, so this is the case. We have a clean system. Like clean system means we do not have any defects into the system. The system is pure. But in reality, the situation could be more difficult, more interesting, in the sense that we have defects in the reality in the system. So let's consider this situation. In this case, in the simplest case, let's consider the defects are single side defects. So what does the defect means? So the defect signifies like we can consider the in a chemically adsorbed media, right? Chemically adsorbed media, chemical medium in which the particles gets attached to the surface on the chemical surface due to the binding energy of the surface. The particles gets attached to the surface. So the in that situation, in that case, the defects signifies some locations in where the binding strength of the objects is so negligible that the objects cannot be attached to the surface. So this is the realistic situation. This is more realistic situation. And what would happen? The question is again the same. What would happen when we have defects in the system? And if we tune the jamming, sorry, if we tune the defect density, which is denoted here by Q, so fraction of lattice sites which are occupied by the defects. So we have 30% of defects in this particular example. We have 30% of the sites are defective sites, and these sites are completely forbidden for the adsorption. But the remaining vacant space, that means we have 1 minus q fraction of lattice sites. Those lattice sites are occupied by the dimers, and in the simplest case, let's consider the situation, the dimers are equiprobable. The orientational, there is no orientational bias. The horizontal and vertical dimers are equally probable. So in that case, by varying q, we can get different jamming densities. The system will be jammed at different filling fraction. And in this particular example, when we have 30% of defective sites in the system, the jamming density is this 0.57. Okay, so it's only, I have only talked about the jamming density and so on, but the more important question is, in the jam, in this particular problem, a transition is associated. It's called the jamming transition, and it is characterized by this way: the fluctuation of the jamming density, and it has been it's how does it scale? It scales as a power law in this manner. So then this exponent nu j, which characterizes the jamming transition. So what we see, what would be the jamming the value of this exponent? Okay, so for q is equal to 0, that means we have a clean system. In that case, it is known in the literature, it should be 1 in two-dimensional case. Nu j 1, 1 by nu j should be 1 in two-dimensional system. But for any other values of q, like let's say here is the q is equal to 0.8, so 80% sites are defective sites, but the 20% sites are occupied by the dimers. In that case, if we calculate this quantity and we plot on a log scale with the system size, you can see this is a completely straight line, and this the exponent of this straight line is close to 1. So again, for different values of q, so irrespective of the value of q, we see that this exponent is universal. And in the literature, actually in the literature, it is known that this exponent is universal in the sense that when it is, and it is only dependent on the dimensionality of the space. So it's actually nu j nu j is 2 by d. So d is the dimensionality of the space. So in two-dimensional, it should be 1. So here we have also observed that. But this law is more robust in the sense that this is true even on the fractal lattices. But in that case, so this dimensionality d is replaced by the fractal dimensionality of the space. So it should be like df, fractal dimension of the fractal object on which the dimers will be, or the objects will be deposited. Well, so we let's consider more and more realistic situation. Like here we considered, like we have some defective sites in the system, but those defects are uncorrelated. Uncorrelated means uncorrelated in space, that they occur randomly in space. But the more realistic situation could be the situation when the defects will have some spatial correlation. This is more natural in nature, in real world. Like we have porous material, and the porosity actually is been observed to follow some spatial correlation, and it's sometimes it could be long range spatial correlation. So what we so we are interested in that kind of system. So what we do, we introduce spatially correlated defective sites into the system, and then we ask, and then we deposit the timers on the remaining vacant space, and then we ask whether the jamming transition and all the other properties would be affected due to this spatial correlation or not. So here you can see on the left, you can see, so this is also a defective system. We have 30% of defective sites. On the right, we also have the same defective system, but here the defects are spatially correlated. As you can see, okay, so defective sites are denoted, sorry, painted here by red colors. So as you can see, these defective sites they form a compact cluster. This is more compact, and it's a spatial situation when the strength of the spatial correlation is 0.4. So what is the strength of the spatial correlation, that I will come to the next slide. But you can see, just distinguish the two pictures. Here the defects are homogeneously distributed in space, but here the defects form some cluster. When we introduce spatial correlation among the defective sites, they form some compact cluster, and we can also quantify that compactness of these clusters. And we have done in order to quantify the compactness of these defective sites, what we have measured, that okay, you can see there are different uh, clusters of defective sites. So among those clusters, we just we just pick the largest cluster, and we calculate the largest cluster of the defective size and how it scales with the system size. And it scales in this fashion: is for q less than qc. Q is the defect density when it is less than a critical value qc. So qc is a particular situation, that is when the defective cluster form pulse. So I will come to this percolation picture more later. So in this case, when q is less than qc, is the system, the defective system, the defect space is in the subcritical regime of the percolation transition. So that means these clusters are very minuscule, and they are not sufficient to form a global connectivity. And global connectivity means there should not be any defective cluster that spans from one end of the system to the another end of the system. So in that situation, if we calculate this quantity, it varies in this way. For random defects, is alpha is equal to 1. So it's quite expected. This is subcritical regime of the percolation transition of the defective sites. So it should be 1, and we get back that particular thing. And when it is strongly correlated, this alpha is more than unity. And if we decrease the strength of this strength of these correlation, we have seen that it continuously, this exponent alpha continuously decreases. If we decrease the strength of the spatial correlation, and it get back eventually to the value 1, which is the case of uncorrelated defects. So we introduce this defect, and then we ask the question, what would happen about the jamming density and jamming transition? So this is the special case. So like here, in this situation, the defects are homogeneously distributed when they are uncorrelated. So they will, while depositing the dimers, they will the dimers will experience lot of screening effect. I mean, lot of attempts will be unsuccessful, and there will be lot of vacant space. But here is compact, so this screening effect will be reduced. So we systematically, what we do, we systematically increase the spatial correlation. Okay, so spatial correlation, and then we see how the jamming density, that means the filling fraction, dimer, how does that vary as we increase, as we vary the spatial correlation strength for different values of the defect density. So this red one is for strongly correlated defective sites, and this is for completely uncorrelated defective sites. So as you can see, for a given value of q, the filling fraction gets increased when we have strong spatial correlation. So this spatial correlation actually helps to pack the system more densely. So I have skipped one slide. This is a technical slide, but it's, I think now it's important to mention. So it's like how we generate this kind of correlated landscape. So we follow this kind of method, which is called the Fourier filtering method. So in that case, we generate correlated random variables, and then what we do, so the correlated random variables, and then let's say it is denoted by this hx, is a random variable, and they follow this kind of correlation function, which is long range in nature. It's a power law correlated, and this gamma determines the strength of the spatial correlation. So what we do, we follow this kind of method and generate the random correlated random variables, and then we associate these random values to the to every side of the lattice. So let's say we consider the one-dimensional picture. So we have this space, and then we have these random variables which are correlated in space. And then what we do, so we can then calculate okay, in order to verify uh, whether this kind of landscape holds this kind of special property or not. We calculate the correlation function, and then we found that exactly follows the long range correlation is on log scale. It's a power law. As you can see, is the gamma value is small, so the decay of this curve is very small, slow, and so this is strongly correlated. So but if you increase the value of gamma, this correlation strength gets reduced, and for gamma tends to infinity, that means it will be decreasing, and in the limit gamma tends to infinity, it will be like Dirac delta function, and we get back the situation of uncorrelated picture. So in this fashion, we generate the correlated landscape, and then we rank these values. So let's say this is the 1, this 2, 3, 4, 5, 6, this way. So we rank these values, and then from 1, 2, 3, 4, this way, from ascending order from smallest to the highest, we keep on occupying those lattice sites until we get back the desired densities of occupied sites of the defects. So this is the special case. Let's say q is equal to 0.3. This is 30% of the defective sites, and gamma is equal to 0.4. So we have these field occupied lattice sites, which are considered to be the defective sites, and then on the remaining vacant space, which is the white space here, on this remaining vacant space, we will be we deposit dimers with equal probability. That means horizontal and vertical dimers are equally probable. So whatever I have talked about until now, this is the situation. And the main question is now, more important question is now, is whether due to the introduction of this spatial correlation, whether the jamming transition, the nature of the jamming transition will be changed or not, or will be universal. We will see it now. So as you can see, so this is the jamming transition is characterized by the fluctuation of the jamming density, as I mentioned before, and it's a power law. It varies as a power law. So in this fashion, so what we do, we plot these values delta L against L on a log scale, and try to see whether they follow a straight line or not. So in this case, when we have spatial correlation, this is for gamma is equal to 0.5, strongly correlated. 0.6, so the system gets going towards the uncorrelated situation when we increase the value of gamma. So as you can see, so there is a small curvature here. So it's not exactly a power law, and it seems to saturate. For strong correlation, this curve seems to saturate towards a value. So we have tried to fit the data on using a modified functional form. We added this constant factor b and tried to fit the data using this form. And here is this plot delta L minus B. So it should follow, if it is the, if is the delta L follows this kind of scaling law, then delta L minus B should be straight line on a log-log scale. And as you can see here, for a particular value of gamma 0.8, we have 4 sets of curve or different defect densities. And you can see this is not unity, it's far from unity, and it's monotonically, continuously varies as we increase the defect density for a given correlation strength gamma. Alternatively, what we can do, we can fix the defect density and we can tune the value of gamma. So small value of gamma is the strong correlation, but when you increase the value of gamma, the system approaches towards the uncorrelated situation. So as you can see, it's a, where q is equal to 0.3, sorry, 0.2. As you can see, it's far, the value 1 by nu j is far below than unity, but it continuously going towards the value unity when you increase, sorry, the value of gamma. That means when you decrease the spatial correlation strength. So this, the introduction of these correlated defects has has some non-trivial effect on the jamming transition. Okay, so I have talked about only about the jamming transition. Let's come to another aspect of this problem, which is called the percolation phenomena. But before going to this part, I would like to ask if you have any questions or not, or you can ask me at the later of the talk. What do you prefer?
Any question from anybody else? Okay, I think they prefer to ask you at the end of the.
At the end. Okay,
Yeah.
so I'm going to proceed. Okay, so let's now talk about the percolation problem, the percolation situation. So what is percolation phenomena? So it's actually deals with the emergence of large scale objects, large connected clusters, connected cluster. So in the literature, we have the two simplest version of the lattice percolation, which are bond percolation and side percolation. In case of bond percolation, the lattice bonds are occupied with probability p, or they are kept vacant with probability 1 minus p, and p is the tuning parameter. By tuning the p, you can tune the number density of the bonds. So if you tune for p is equal to 0, if you ask the question, okay, whether there will be a percolating path or not, what is the percolating path? Okay, you can consider these occupied bonds are the metals, and the unoccupied bonds are the insulators. So it's a metal, and the system is a metal and insulator mixture. It's a mixture of metal and insulator. And if you put the system and then apply a potential difference, so the question is whether the system will be in the conducting phase or not. Well, so in order to have the current through the system, there will be a metallic path that connects from this end, one end, to the other end of the system. So that is of course dependent on the value of p. So if we tune the p, it is observed that at a particular value of p, the system starts conducting. And you can see, of course, before that value, so it's that particular value is called pc. Pc is the percolation threshold of the system, and on the square lattice is exactly known, it's half. So if p is less than pc, the system will be in the non-percolating phase, that means insulating phase. There will be no current through the system. But if p is greater than pc, the system will be in the percolating phase. That means there will have at least one connected cluster of these bonds that connect one end of the system to the another end. So this is the percolation problem. Is as you can see, is all about the problem of connectivity, global connectivity. Global connectivity means this the connectedness of one end to the another end of the system. So this is the bond percolation, and here is the side percolation. In case of side percolation, instead of lattice bonds, the lattice sides are occupied one by one, and in that case the PC is not known exactly, but it's known numerically is 0.59. So this is the situation of the percolation. It's a phase transition. In one phase, the system is in the conducting phase. Then another phase, the system is in the non-conducting phase. And at PC, it's a particular value of P, which is called PC. At PC, the system undergoes a phase transition, and it's known in the literature that this transition is continuous in nature and is universal in the sense that this kind of this bond percolation or side percolation or the geometry of the lattice, those small details are irrelevant, and the system shows some universal behavior. Universality in this context means the critical exponent associated with the phase transition is universal. They remain same. If you change the small details of the system, they remain unaltered. Okay, so in this context, in our context of the random sequential adsorption, we can also study the percolation problem in the following fashion. So what we do, starting from an empty lattice, we occupy the lattice sites by the defects until we have a certain fraction of defective sites, desired fraction of defective sites. And then on the remaining vacant sites on this space, we occupy one by one, we occupy the lattice with the dimers with equal probability. That means vertical and horizontal orientations are equally probable. And then we wait until the system reaches the jammed state. And then we ask the question whether the system will be in the percolating phase or not. Well, this answer will be dependent on the defects, the defect densities, and okay, while we are studying the percolation, we are studying the percolation in the jammed state of the system, and percolation means percolation through the sites occupied by these dimers. Okay, and in this context we have two important properties. One is, okay, as you can see, in terms of, in case of this kind of correlated of defects, these defects form some kind of island. This whole vacant space gets fragmented into pieces and into several islands. They form several islands, and these islands, all these islands do not take part in the percolation, do not help to achieve the system to lead to the percolation point, because in this case what is relevant is the largest vacant space, the largest vacant space, which is the most important quantity here. And if we study what are those the sizes of these other vacant spaces, except for the largest vacant space, they follow some broad distribution for strong correlations. As you can see, this black one is for gamma 0.4 is strong correlation, and for point, and we reduce the correlation systematically like 0.8, 1.2, 1.6. So this distribution of this vacant space, void space, gets narrower as we decrease the correlation strength among the defects. And in case of completely uncorrelated case, is even more narrower. This kind of, we do not observe this kind of broad distribution. Another case, as I mentioned, like in case of percolation, which is important, is the average size of the vacant space, maximum largest cluster of vacant space. So we are interested in how it scales with the system size, and we found that it scales with the system size in this fashion. And this a if you see these values for different values of gamma, a systematically approaches towards 0. So for completely uncorrelated case, it should be, a should be 0, and this should scale with b times l square in 2 dimension. But in the presence of strongly correlated defect, this gets modified and it follows this kind of scaling law. And now see how this kind of details are important in terms of percolation transition. And our main interest is whether due to this the introduction of these spatially correlated defects, whether the percolation transitions is is affected or not. So what we do, so again, as I mentioned, we for a particular defect density, we wait until the system reaches the jam state, and we ask the question whether the system is in the jam state or not. So here we plot the probability of the system to be in the percolating phase for a different by varying the value of q. So of course, when Q is equal to 0, the clean system, the dimer density will be so high at the jam state, the dimer density will be so high, the system will always be in the percolating phase. But if we increase the defect density, at certain point, we will observe that the system will go towards the non-percolating phase, and there is a phase transition from the percolating phase to non-percolating phase. So in this regime, this particular point, this percolation point is denoted as QCJ. So in this regime, all the jammed configuration are percolating, and in this regime, when Q is greater than QC, all the defect space, the defect sites, they are percolating. But in between these two limits, these 2 points, the system do not percolate either through defects or not through the dimers. So we were interested in this region, this the transition at this point, whether they are universal, they fall in the random universality class or not. And you can see we have done some finite size scaling analysis, and this is the case when gamma is equal to 0.8, the spatial correlation strength, and this you see is 0.4. But for random defect, it is this value 1 by nu p is 0.75, and so it's far beyond that universal value. And you can see we decrease the correlation strength. So it's for weak correlation, little bit weak correlation compared to this. So 1.5, and we get back, we get this exponent 0.662. So in this way, by scaling analysis, we have calculated this exponent 1 by nu p by systematically varying the value of gamma. As you can see, so this is a monotonic function of gamma, this exponent, and when it goes towards the uncorrelated situation, like higher value of gamma, it is approaching towards its universal value, which is 0.75. So this the introduction. So what is more important here is that we have only spatially correlated defects, but this remaining vacant space, on this remaining vacant space, we are depositing the dimers randomly, completely randomly. But these defects are sufficient to change the universality class of the percolation transition through these dimers. Okay, so this is all about the percolation transition of the jammed state. But in this particular phase, when the jammed configuration are percolating, so we can ask that, okay, one by one we are depositing the dimer. The system will be in the percolating phase before going towards the jammed state. The system will be percolating before going towards the jammed state. So what about that percolation transition? So for a given value of Q defect density, what we do, once the defective sites are there, 10% defective sites, one by one, we occupy the lattice sites by the dimers, and then we ask the question, what is the probability of getting a percolating path through the dimers? And of course, this is the density of the sites occupied by the dimers, this P. And then this is the percolation probability. As you can see, this is the point where the percolation transition occurs. And from the finite size scaling analysis, we calculated the critical exponent. And in this case, we can see on the critical exponent is far beyond the 0.75 value, is 0.48. is for gamma is equal to 0.8 and q is equal to 0.1. So only 10% of defective sites are sufficient to change the universality class of the percolation transition. And here it's 0.8 and its defect density is 0.3. We found other different critical exponent which is far beyond 0.75. So it systematically varies. If we tune the value of q and gamma, it systematic this exponent systematically varies. So the main summary of this percolation in this case is this spatial correlation among the defective sites has profound effect on the percolation transitions of the dimers. Okay, so this is all about my talk. I just wanted to sketch another interesting thing, which is like here we have studied the spatial situation when the the defects are single sites, but we can consider in more general situation when or except for this single defective sites, we can consider some extended defective sites, defective objects on the lattice. So we can consider like, okay, we have this kind of square shaped defects in the system, and we ask the question, how does this kind of percolation threshold or percolation universality, we can study this kind of question, the same set of questions that we have studied before. So what we have studied is that, okay, so let's consider this kind of square shaped defect, and then consider the occupation of monomers, only the random percolation thing, that monomers, this one side, not the dimers. The simplest situation is monomers, and it's a uncorrelated defect. So these defects are uncorrelated in space. So what happened about the percolation threshold of the monomers? And we see that if we increase the density of these defects, or if you increase the size of the square shape defect, the percolation threshold gets reduced. So it should be like a side percolation scenario in the presence of square shape defects, but we get back we get the values of the percolation threshold which is well below 0.59. So 59 is the side percolation threshold on the square lattice. So when f is equal to 0 means when we do not have any square shape defects, we get back this situation. But when you increase the defect densities, we can see. So in this case, the defects are occupied in an uncorrelated fashion, but we get back that the system is gets percolated even before 0.5, when the defect when the monomer density is much below than 0.59. So this is a problem which is important in the context of in engineering context. Like I can tune certain properties of the system, and we can manufacture highly conducting materials, tunable, and the conductivity can be tunable. So in this fashion, by introducing defect, we can tune various different properties which are related to conductivity. So let me now conclude my talk. So what I have talked about is related to random sequential adsorption, and I showed the results which are in the context of spatially correlated defects. So we are mainly interested in the question whether this kind of spatial correlation would be important in changing the jamming and percolation transitions or not. And we have seen the spatial correlation has profound effect on the jamming and percolation transition. Specifically, only a finite fraction of defect, like 10% of correlated defects, are sufficient to change the universality class of the percolation transition that we have evidenced. Here is the reference of this paper we have, and for further details you can see this reference. And finally, I would like to thank the audience for your patience and your attendance.
Thank you, Sumanta, for a nice presentation of jamming and percolation transition.
Thank you.
So students are waiting with their questions in the chat box. So let me read this.
Okay.
One question from Shovik. Is jamming coverage, say for a 1D lattice chain, unidirectional or completely random?
Sorry,
So,
in one dimensional, what I could not get that particular term unidirectional, the phrase unidirectional
so
word.
Shovik,
So
can
I
you
don't
please?
know what the meaning of
Yes,
this
sir.
unidirectional.
Actually, I wanted to mean that jamming coverage, we can see the expression, right? That P at T tends to infinity. That is actually the expression of jamming coverage. My question is that what kind of coverage is actually this? Can it be actually random? Or how can we choose
Well,
that
yeah, we are
how this coverage can
depositing dimers randomly in
A-
space.
Okay,
And
okay.
in one dimension, it should be unidirectional. There is no other direction, as I guess.
Yes, yes,
Yes,
as I
yes,
mentioned,
yes.
there is no other
In one
direction.
dimension, it should be unidirectional. Yes, but in case of if we increase the
Yes,
dimension,
yes.
then it can
Yes.
be random.
Yeah, yeah. Like here in two dimension, we have 2 degrees of freedom. One is horizontal and vertical.
And next question is from Shomrat. Can you kindly throw more light on why the largest cluster of void space is important for percolation of absorbed dimers?
Well, okay, sure. Okay, so we are studying percolation through the sites occupied by the dimers, right? And percolation through the site, I mean, in case of like site percolation, like two neighboring sites, when they are occupied, they belong to the same cluster. So in that case, if this space, let's say this space, if this space is completely surrounded by the defects, so this particular space will not be helping in achieving the connectivity from one end to the other end of the system, right? We need to consider the uh, connectivity through the dimers. So this particular space will not be taken care of because this is surrounded by defects. And
Okay.
the largest cluster, yes, yes, and the largest cluster is important because the largest cluster only take part will be the relevant quantity in terms of the percolation.
Okay.
One more question from Professor Urunaho Chakraborty. What is exactly meant by correlated defects? Does it mean that the cluster size at one part of the lattice is somehow related to the cluster size at another place?
Okay, so the question is about the what is this correlated defects.
Defects. Yes.
So random defects means when we occupy the a particular site, the next occupation of the lattice site by the defects is completely independent of each other. But here it is dependent. Once one particular site, once there is a defect on a particular site, the next site will be occupied or not by the defects. That is a dependent quantity.
Okay. Just does it mean that, say, if I give you a rule that whenever a site, whenever some places will be occupied in your lattice, they will be occupied in pairs, for example, always. So that it is definitely a kind of a correlation, right?
Of course, this is the kind of a correlation, but that is short range correlation.
Right. Definitely. Yeah.
Mm-hmm.
Short range
But
correlation. True.
short range correlation, if we introduce only short range correlation, the
I don't.
universality class does not change.
Yes. Yes. And no, I don't think anything serious will happen in that case for short range
Mm-hmm.
correlation.
Exactly.
But in that case, Sumanto,
Mm-hmm.
is there a way to define exactly how big should the range be? I mean, so what
That is
range you
an
call short range? I mean, so if it is three sides, it is still short range. Okay.
I understand. This is very important question. I think okay. So there is one answer that we tried to find out. Like here, even it's long range.
Yeah.
So here we tune the value of gamma and we calculate the jamming density. Or in
Mm-hmm.
that, in the other case of percolation transition, like here, so the system is going towards the uncorrelated situation, but still we have a long range correlation. So what would be the scenario? Means why there is long range correlation, but it's weakly correlated. So
Okay.
what is the most important quantity here? So we try to formulate one particular thing
Mm-hmm.
that is called extended high risk criteria.
Okay.
But extended high risk criteria says that if gamma is less than 1.5, then the system will behave as uncorrelated fashion.
Okay.
But here also we have seen that even on when it is 1.5, the exponent is not the random, the exponent does not coincide with the random uncorrelated defect situation. So there is something more, and I and
Mm-hmm.
I do not know still now what is
Okay. Okay. That's fine. Okay.
the main cause of this.
Okay. Thank you very much. It was very nice talking with you.
Thank you so much.
So I do not find any more questions. So I have a question, Sumanta. So
Yes,
suppose
yes.
you are working on monomer and you are trying to see the jamming coverage. So it is 100%. Okay. So according to your description.
Yes, the lattice will
And
be completely filled. That is true.
yes, yes. And if you use the dimer, it is 90%, around 90%.
Exactly.
Okay. And suppose you are increasing the number of atoms in a KMR, in a polymer, and is there any systematic variations of the surface coverage as you increase the number of atoms in the KMR?
Yes. There is some expression, but it's based on some
It
numerical
will
figure.
decrease. It will
Yeah,
decrease
yeah.
certainly. Okay.
It will be it is a decreasing function, but of k. Let's say k mar. So it is a
Yeah.
decreasing function of k
K.
up
Yeah.
to certain value of k. Okay,
Hmm.
then it start increasing because when you let's say k mar. So we have the exploded volume interaction,
Hmm.
okay, but when you increase the k, the length of k, that means the nearest neighbor sites are all be occupied, right?
Hmm.
So so of course it so decrease is explained by the exploded volume interaction between the objects. So when you increase the length of k, the exploded volume interaction will be increased, but at the same time there is another mechanism that helps to increase the filling fraction, that is because of
Increasing number.
consecutive, yeah, consecutive lattice sites. We have more and more consecutive lattice sites, those are occupied, so there is a
Hmm.
two competing mechanism, and
Okay.
in
Right.
this case
Right.
it saturates
So there will
somewhat.
be critical K for which it will be minimum for the
Yeah,
surface
it's a
coverage.
minimum, and it is like 32 or something. I cannot remember at this moment, but
Okay.
it's like that.
Okay, thank you. So let us thanks the speaker again for a beautiful presentation of percolation and jamming transition. Thank you, Sumanta.
Thank you so much. Thank you.
So Shovik, please take the charge of.
Yes, thank you, sir. And on behalf of the ICCMSP team, I would like to thank Dr. Sumanta Kundu for delivering such a illuminating and interesting talk. And without making further delay, I would like to shift to the next session, which is oral presentation. There are two oral presentations, so I would like to request Somrat to take charge of this session and introduce the speakers. So over to you, Somrat.
Thank you, Shovik. Am I audible?
Yes, you are.
Yes, you are
So
audible.
the rules. Absolute. Good afternoon, everyone, and once again thanking Professor Kundu for the previous marvelous talk. So here,
Thank you.
this is
Thank
the
you.
last oral presentation session. The rules remain absolutely same as it was in previous. Thus, each of the speaker will be given 15 minutes for presentation, and 5 minutes shall be the question and answer round session. So I request everyone to put the question in the chat box and everyone to remain muted during the presentation. we will answer the questions after the presentation is over. So the first speaker in this round is Miss Shayoni Pal from Indian Institute of Science Education and Research, Kolkata. Uh, Shayoni Pal, Miss Shayoni Pal, you can go ahead.
Hello.
Hello, yes, you are audible.
Okay. So should I start
Yes,
my
yes, you can
presentation?
start.
Okay. Thank you.
You can present your screen also.
Ayani, are you presenting?
I think she's muted right now for some reason. Uh, can you hear us?
Yes, I can hear you. I'm just trying to
Okay,
present.
okay, 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 okay. Take your.
Mhm.
Your screen is visible? Yes, absolutely. Okay, you can go.
Hello.
Yes, yes, it is fine. Please
Yes,
carry on.
yes, you are audible. You can start.
Okay. Okay. Thank you. So good afternoon, everyone. I'm Shani from ICCMSP, Kolkata. I'm a PhD student here. So in our lab, we actually work on with this VNA FMR spectroscopy setup. So we do study magnetization dynamics here. We use ferromagnetic samples for our measurements. We do room temperature and low temperature measurement as well. And actually, it is not a, commercial setup we use. This is completely built in our lab, this spectroscopy setup. So there, a very important and an integral part is this coplanar waveguide. This is actually a microwave device. So how it works, how the coplanar waveguide, what's the use of it in the setup, and like how we have designed and fabricated, and now we are measuring with this. So how this all have happened, that I'm going to talk today. So basically the coplanar waveguide and the whole setup. So this is the outline. This is how I'm going to present today. So first of all, I will discuss actually why magnetization dynamics is so important now, why we are studying that. Then the general introduction uh, about this dynamics and the like the measurements, how people do. And then the core part of the talk, that is the instrumentation part. So there I will mainly focus on the microwave device we have designed and using it now in the setup. and then the sample we generally use, and the standard sample for the instrumentation to uh, uh, like uh, in the year we use. We first of all used this sample. That part I will go through, and then the some very few results and discussion I will talk about, and then I will conclude with the projects I already have done with the setup, the ongoing projects, and the new later possibilities with the instrumentation, like the setup. So first of all, why to study magnetization dynamics? So as we know already that magnetism, magnetization, magnetic samples, these are like very old topics to uh, discuss, because we have already studied this in our textbooks. We used in our daily life, like in hard disk drive, like in different laptops, in mobiles, in different like in microphones, everywhere actually. In our daily uses, we use this phenomena, magnetism. So what new to it is the possibilities of the different kind of thin films, nanostructure, multi-layers, magnetic multi-layers. We can now fabricate these things in our lab. So that is the new techniques we come up with. That's why studying these thin films, nanostructures, these have actually raised the interest again to study in this field. So magnetization dynamics in this kind of system is quite new to us. And one of such discipline that actually that has a great impact of our electronics industry is spintronics now. So that's kind of a that's kind of a discipline that actually interplays between this magnetization and spin transport. So that part, and obviously the like whatever we are using now, whatever magnetic devices or storage media or field sensor we are using now, we need more like faster devices, we need smaller devices with less power consumption. So that is the industrial interest to it. So and why we have used fmr to study magnetization dynamics, that is because fmr is a very well established and well studied experimental technique that we can rely on to characterize the properties of magnetic samples. That's why FMR, ferromagnetic resonance spectroscopy. And but there was some old techniques for FMR spectroscopy. We have replaced it with new versions, like we have used vector network analyzer. That's why I wrote VNA FMR spectroscopy. And then this CPW we are using. CPW we have fabricated. That is a new addition to the old kind of spectroscopy setup. So I briefly will say what the existing uses in industry, that is magnetic sensors we use, magnetic recording heads, and storage devices like in hard disk drive. These are all like very use of the magnetization property magnetic system. And the advanced possibilities now is these two I have mentioned, spin transfer torque, RAM, and MTJ sensors. These are very new to the market, we can say, because these actually based on the new studies regarding the magnetization dynamics in thin films and nanostructures. So these two are very good example for that. So, and in basic research, spintronics is one such research area where very like um, where where new studies have been done, and it's a very hot topic to research on, I can say. I have just mentioned three of the three of the streams inside this huge spintronics, that is spin pumping, inverse spin Hall effect, spin transfer torque. These three actually I have mentioned because few parts of these three we have already studied with our existing setup, and few we are going to do. So that's why these three only. And as I have mentioned, that spintronics actually plays between this magnetization dynamics and spin of the electron, like the spin current. That is, if we can see from this figure actually, that how magnetization like spin current, how spin current modifies magnetization, and how magnetization actually creates spin current. So this is a very good example of that, that how magnetization dynamics affects the whole spintronics industry and spintronic research, sorry. So now I will give a general introduction to magnetization dynamics. So this is a phenomenological description, of course, of the magnetization dynamics. So as we know that when we have a ferromagnet, so there is there is magnetic moments of the ferromagnet. Now, if we apply an external magnetic field to the system, that external field will magnetize the sample, and due to that magnetization and field will be generated inside the material, and the combination of this external magnetic field and the magnetic field due to magnetization, these two will combine, and a net magnetic field will be inside the magnetic field. Let's say H is that magnetic field, and M is the magnetic moment of the ferromagnet, we can say. So what happens is, when we just apply the magnetic field, the net magnetic field, let's say H, the magnetic moment of the ferromagnet will start to precess around that field. And if there is no energy loss in that process, then this precision will last for infinite time. That we can see from the first figure, like A, and the first term in the right hand side of LLG equation. So that actually describes how it will precess. But it's not like it will precess for time, because energy, like the system loses energy. So that precision doesn't last for long. So in that case, how the relaxation affects the like how the dynamics changes when the relaxation, we add the relaxation, that part we can see from the second figure and the second term in the right hand side of LLG equation. So there, this torque term m cross dm dt, that actually shows that how the precision like stops, and how that magnetization or the magnetic moment aligns with the H field. So this is the very basic idea of magnetization dynamics, and alpha is very important here. Alpha is the Gilbert damping coefficient here, which actually shows the which reflects the relaxation of the system. So this part I will talk about detail, talk in detail after a few slides. So this is the very basic thing of dynamics, magnetization dynamics. So this is, we know that magnetization dynamics is this, but how to probe that? Like how to know that what is happening there, how to probe that? So for that part, we need this magnetic field, that is RF field, that is the microwave field we use in spectroscopy. So when we apply a magnetic RF field perpendicular to this net magnetic field, that is H, if we apply it like in the direction of let's say in the Z direction, H is in the Z direction. So if we apply in the XY direction, in the XY plane, if we apply the magnetic field perpendicular to the magnetic field, not magnetic field, microwave field, so perpendicular to the H field, and if the frequency of the microwave is equal to the Larmor precession frequency, Larmor precession is the precessional frequency of the magnetic moment. If that happens like perpendicular and equal to the Larmor frequency, if that condition satisfies by the microwave field, then we will get an absorption, like the system will resonate, and maximum absorption of the energy of the microwave energy will be like maximum absorption will be there for by the system. So that we can see from the FMR absorption spectra. So this is the right hand side. We can see the typical FMR absorption spectra. That is the that is what happens when the condition matches, as I already said. So this we got in our system. So this is broadly the magnetic resonance is all about. So then this is the basic configuration of a FMR spectrometer. This is like people does that for a long time. So the important parts in this spectrometer system is we need a microwave generator which will supply the RF field, and electromagnet which will supply the external magnetic field, and the of course the um, sample ferromagnetic sample we are probing, and the in the heart of the whole spectrometer setup there is this resonator we can see, the red one inside the electromagnet, the resonator we can see. So we actually replace this resonator with the CPW. So why we have done that and how, that I'm going to discuss. And another important thing here is to notice is that uh, uh, in our setup, as we have used vector network analyzer, which is actually a microwave generator as well as a detector. So we have replaced the whole part except the electromagnet with a VNA. So that's why people uses VNA nowadays, because of its brilliant I can say use in this particular case, spectroscopy. So then the instrumentation part, mainly the coplanar waveguide design and what is it, that I'm going to discuss. So this is a microwave device. This is a planar microwave device, or we can say 2D microwave device. So it replaces resonator in our case, but it has many other applications in microwave engineering. We have used used it in this way. So as we can see, CPW is actually two layer of, there is two layer. One is substrate, or we can say the dielectric layer, and another one is the, on top of the dielectric layer, there will be a metallic layer, or the copper layer. Generally it's copper, because the industries those create like produces this PCB laminates, they actually use this copper. So this is that only, that PCB laminates only, these are. Then what we do is we cut the metal layer according to our design, and we get different shapes of the CPW according to different use of it. So for us, there was two options. One for a transmission measurement, where there is there could be two port, or another possibility was the reflection measurement, where we can just use one port for the whole measurement. So we
Excuse me,
use the
sorry to
second one.
interrupt. Excuse me, just sorry to interrupt you. The 15 minutes is up. I will request you to wind it up as soon as possible. Okay. Fine, you
Yes,
go
yes,
ahead.
yes. Of course, of course. Okay, so these were the advantages of the short circuited CPW, as I have already mentioned. Because we are using the low temperature measurement, that's why reflection geometry for the FMR was very useful for us. That's why we have used it, and the flexibility of the design. This is our home built optical lithography technique for fabrication, and the middle part where the all the parameters I have written, these are actually from line calculator. We find out the specifications, specifications, and this is the fabrication, after fabrication. And this is a simulation when after fabrication, how it will work when we will send microwave signal through it. So that's why we have done the simulation using CST Studio software. So this is a simulation, and we find out that where the exactly the magnetic field will magnetic field intensity is maximum, that is the red part. So we always ensure that the sample is on top of this part only. So then the whole low temperature setup, where we can see how the inside the cryostat we have put the sample like on top of the CPW. We just flip the sample like thin film, obviously the thin film sample we put, and then we apply the magnetic field, external magnetic field, and the microwave through the coaxial transmission line, and VNA does that, and VNA detects that too. The result also detected by VNA. So this is the details of the sample, like Parmala, the standard sample we have used for our measurement, so that we can compare it with previous and commercial spectroscopy setup. That's why we have used Parmala. And this is the ephemer absorption spectra. We got it from our setup actually in reflection mode. We find out this. For different frequencies, if we applied magnetic field, external magnetic field for different frequencies, we will get this kind of absorption. And from the line width and from the position of the absorption, like position in the sense the resonance frequency and resonance field, these two are very important. Three things are important here: resonance field, resonance frequency, and the width of the absorption spectra. These three actually have been used for the calculation, the results. The Gilbert damping coefficient, as I have already talked about, so this was very important to find out how the relaxation goes on inside the sample or the material. So this is the equation we fit. Like this is a very well-known equation to fit for line width versus frequency, resonance frequency. So from that we find out the results for temperature 7.5 K and temperature 300 K, room temperature and low temperature. And these values very much is in good agreement with the previous and commercial spectrometers. Then this effective magnetization, this is the Kittel formula, where we have fitted our data, and just like the previous one, we have measured it at low temperature and at room temperature, and we found out the data which matches the commercial one. So we can say that we successfully have obtained the magnetic parameters using our short-circuited CPW setup. And then this is the just to ensure that yes, we are using the right spectrometer. So then we have studied temperature variation of alpha and M effective in the whole range of the whole temperature range, and we have reported it recently. So that study has been done, and some good phenomena we came like. Then we have done this bilayer devices, tungsten ferromagnet and topological insulator and ferromagnet, to study the interface. There we have this spin pumping effect we find out, and that a little bit of spin pumping effect was there. So that part we have to we have to do more on that. And finally we are targeting to integrate electrical measurement facility with this existing one, so that inverse spin Hall effect and spin transfer torque can be these studies can be done in our system. So that's our goal to for further studies. We are thinking these things. So that's all I have to talk about. So acknowledgement from the I get my fellowship from DST. So thanks for the financial support, and my supervisor and my lab mates, and Dr. Parthu Mitra and Professor Parthu Pratim Sarkar. I want to thank specially. So that's all. Thank you.
Thank you for the very nice talk. There are two questions which I will answer one by one. The first question is from Sovik. That is, the FMR usually works in microwave range. In the entire system, what is the significance of using the microwave generator? Is it just to tackle with that frequency range?
Yes, that frequency range, because uh, gigahertz is the range where this magnetic resonance, and we study in that region. So if we want to probe the system, then and the magnetic field we have used magnetic field in the range like 50 oersted to 500 oersted. So in that region, when we apply the magnetic field, the resonance is actually happens in that microwave region, like from 2 to 6 gigahertz microwave region. So to probe that, we need microwave generator.
Okay, thank you.
Okay,
There is
thank you.
another question from Shomodip. That is, can we use this technology for cloud storage?
For
Cloud storage for the, I think the memory purpose is referring to.
I understood, sir. Like this particular spectroscopy arrangement you are saying.
Shomodip, do you meaning that only? I believe. Yeah, Shomodip is meaning that. Yes, for this particular.
I'm not very sure, sir, because this is just to understand the system. Like the magnetization dynamics is what is happening inside the system. So this is not a technology for any kind of application. This is to know about the system. So that part I'm not very sure. Like
Okay,
yes.
thank you very much for this nice talk. I will request each and every participant to upload their slides in the Slack channel, because that will be a reference for all of us, and the questions can be attended even after the presentation session. So
Oh, of course, of
thank
course.
you.
Mm.
You can
Thank
now.
you.
So our next speaker in this round, and she's the last speaker of this round, is Reshmi Roy from Calcutta University. You can go next. You are the you can share your slides.
Okay. Are my slides visible?
Not yet.
Okay. No, I think.
Now it is visible, but it has opened something else.
Is that okay now?
The screen has presented. You can show your slides, display your slides.
Okay. So, good afternoon, everyone.
Oh, excuse me. You need to open
Okay.
your slides. It is the Google Meet interface is being shown on the screen.
I am showing my interest. Then,
I would suggest you can go the full screen present, and then you can
Yes,
go to the
if you need to show the whole screen, that will be better.
I think this
I think your slide you are sharing the Google Chrome only.
Yeah, now it's okay. You just cut
Yeah,
the
yeah.
slide. Yeah,
Go to
absolutely.
screen.
Okay.
thank you.
Go ahead. Thank you.
Good afternoon, everyone. First of all, I want to thank the Physics Department of Presidency University for giving me this opportunity to present my work here. Today, I'll be talking about non-equilibrium dynamics in Ising-like models with a biased initial condition. The work is done under the supervision of my advisor, Professor Parampomashan. Classical spin models have no intrinsic dynamics. In order to study the stochastic time evolution, we use certain dynamical rules which maintain the detailed balance. So in our work, I have studied the dynamical fixed points of the zero temperature global dynamics and analyzed the stability of these fixed points. Based on the study of this fixed point, we have obtained a phase diagram for generalized water model also, and we have done some analytical calculation and some numerical simulation for both the mean field case and short range model in Ising model. And related study is the exit probability, which I have studied in different two-dimensional lattices, and we obtained a data collapse for different system sizes, and we have investigated the universality of the scaling exponent and the scaling factor. So Hamiltonian of the Ising model is given by h equals to minus j sum over ij sigma I and sigma j. To study the ordering in this Ising system, zero temperature quenching is used, which is essentially lowering the temperature from a very high temperature to zero temperature suddenly. So Glauber dynamics is one of the popular choices, which is used for zero temperature quenching in Ising system, which is essentially a energy minimizing scheme for a single spin flip. So if a single spin flip, then if the energy change is denoted by delta E, and if the change in energy is negative, then of course the spin flips. If the change in energy is greater than zero, then the spin doesn't flip, and if the change in energy is zero, then the spin flips with probability half. And if we use zero temperature global dynamics in Ising like system in one dimension, we always end up with a ground state that the system ends up with a true ground state where with a consensus where all spins up or all spins down. In two-dimensional case, the ground state can always not be reached. Some of the two-third of the cases, the system will reach the true ground state, but for the remaining one-third cases, the system reaches a stripe state, and it's frozen into that stripe state and cannot get rid of that. And for dimension greater than 2, and true ground state can never be attained. Always striped or blinker states are attained. So I have used a master equation approach to study the dynamical fixed point of these dynamics. So first we consider to study this ordering that a system has a x fraction of upspin initially, and here z denotes the coordination number. That means a spin interact with z number of neighboring spin. So for two neighboring, upspin flip when it has two neighboring down spin, as x is the fraction of upspin in the system, so 1 minus x is the fraction of downspin in the system. So upspin flips when it has two neighboring downspin, so the probability that a spin has two neighboring downspins is 1 minus x into 1 minus x, and a spin with flip with probability half when it has one upspin, one up down neighbor and one down neighbor, and the probability that a spin has one up neighbor is x and one neighbor is multiplied by 1 minus x, and it can happen in two ways, and for each of the cases the spin flips with probability half. So the total probability that upspin flips will be summation of these two particular probability, that is 1 minus x square plus x into 1 minus x, and similarly p minus is the probability that downspin flips. And the evolution equation will be given by dx dt equals to 1 minus x into p minus of x into p plus, where 1 minus x is the fraction of downspin, p minus is the probability that a downspin flips, and similarly for the upspin. And putting the values of p1, p plus and p minus, we get that dx dt equals to 0. Here I have not used any particular steady state condition, just putting the values of x1 and x2, sorry, p plus and p minus, we get that dx dt equals to 0, and that is x0 say. So this the x is over configuration average actually. It means if we start from a, if we take different configuration and evolve zero temperature quenching dynamics, the dynamics conserve the magnetization. So we take a large number of configuration, and after the evolution we can check that total magnetization is conserved. But this is not the case for z equals to 4 and z equals to 6. Z equals to 4 means a spin can interact with 4 neighbors. So here similarly p plus and p minus is defined. So p plus is the summation of our four probability term, that is the first one is if a spin has 4 neighboring down spin, and it can have 3 up spin and 1 down neighbor, and then it can have 2 up neighbor and 2 down neighbor, that's all. And similarly that way p plus and p minus is defined. In that case the master equation will be dx dt equal to minus 2x cube plus gx square minus x. So here the dxdt is not zero. If we put the steady state condition, implying the steady state condition, we put the dxdt equals to 0, and the solution of which will be x star equals to 0, 0.5 and 1. So we get three solution of the steady state condition. And now we have to check what is the stability of these fixed points. So to check the stability, we will consider small deviation from the fixed points. So when we consider x star equals to 0 and 1, putting x equals to x star plus delta t, we will get that d delta dt equals to minus delta for x star 0 and 1. So delta t gives the expression that delta t equal to delta 0 exponential minus t. These negative exponents suggest that the x equals to 0 1 and 1 are the stable fixed points. But when we use x star equals to 0.5, then we can see that delta t equals to delta 0 exponential half of t. And as this is a positive exponent, so x equals to 0.5 is a unstable fixed point. And similarly, the case for z equals to 6, implying we have checked we did the stability analysis, and we get the expression for delta t equals to delta 0 exponential 7 by 8t. It is to be noted that the for z equals to 4, the exponent was half, and for z equals to 6, the exponent is 7 by 8. That means the dynamics are much faster in this case. So the as the dynamics is faster, so the consensus is achieved more rapidly as z, that is the number of neighbors, increases, the dynamics becomes faster. And in this figure, I have shown a flow diagram for Ising model, where it for mean field case for z greater than 2. So here x equals to 0.5 is the unstable fixed point, and x equals to 0 and 1 are the stable fixed points. These were the analytical results, and to verify these results with the numerically, I have consider delta t, where delta t is x minus 0.5, where x is the initial where x is the fraction of upspin, and we have started from a x0 initial fraction of upspin, and we have tried to check how delta t varies with time, and we get exponential behavior in the analytical calculation. So here I get similar exponential variation for z equals to 4. The first picture is for z equals to 4, and these results are for different delta 0. As delta 0 increases, the saturation is saturation is attained much faster, because the system is more ordered to begin with, and the system firstly it shows a exponential variation with time, then it attains a consensus. And as we get delta t equals to delta 0 exponential minus t here, so we can get a data collapse by plotting delta t by delta 0. So this instead shows the data collapse, where I plot delta t by delta 0 against time. So here the exponent is nearly equal to 0.5, which agrees well with the analytical result. Next, I have done simulation on the same system where z equals to 6. That is, our system can a spin can interact with its 6 neighbors. Here we get a same exponential behavior, but the power law exponent is different. In our analytical case, we get the exponent 7 by 8, which is 0.875, but for in the numerical simulation, we get the exponent which is nearly equal to 0.86, which agrees well with the analytical results. So here I have considered the mean field case, because the neighbors were chosen randomly. I didn't include any nearest neighbor interaction here. We just selected a spin, and the spin was interacting with some neighbors, some 6 neighbors or 4 neighbors, depending on the value of z. But now we'll consider the interaction with its nearest neighbor, and we try to verify the result with short range interaction on lattice in Ising system. For the first picture, where I have shown the square lattice interaction in square lattice, where an Ising spin can interact it's with 4 nearest neighbor, and for the mean field, because we are getting a exponential variation with time, but here delta t shows the power law variation with time, in contrast to the mean field case, and it shows a power law behavior in time with an exponent nearly equal to 0.5. To check the dependency on the nearest dependence on the number of neighbors, we have also conducted simulation on the triangular lattice. So here, though the z is different because the in triangular lattice number of nearest neighbor is 6, we get a similar power law behavior, but the exponent is same as the square lattice case, is nearly equal to 0.5. For the simulation, we get 0.46, where delta 0 equals to 0, where delta 0 equals to 0.01. Next, we have conducted simulation with in the square lattice with considering moon neighborhood, when a spin can interact with its 8 neighbors, that is its nearest neighbors, and plus their next nearest neighbor. And we have considered that Z1 and Z1 and Z2 are to be equal in strength. And here we get similar power law behavior, same as the square lattice case and the triangular lattice case. Next, we have taken a cubic lattice where the number of neighbors is same as the triangular lattice, but the dimensionality is different. Here the dimension is 3. And here we get a power law behavior, but the exponent is different. Here the exponent is power law exponent is 0.7 in the cubic lattice case. We can conclude that in this case, though the number of neighbors are same, the exponent is different. So the power law exponent just depend on the dimensionality of the system, not the coordination number or the number of neighbors that spin is interacting with. But for the mean field case, the number of neighbors was important. So the analytical, we know that for all dimension in the ordering process, the absolute value of magnetization shows a power law behavior for short range interaction in Ising model. So, and if we take a magnetic system, and this domain grows as to the power eta d, where d is the dimension and eta is the domain growth exponent, the magnetization is over the sum of all domains, that sum over xi, where xi is the uncorrelated random variable, and xi will varies as to the power eta d. And the stochastic variable m of average over m will be 0, and m squared varies as to the power eta d. So for from them we can see that absolute value of magnetization varies as to the power eta t by 2. Eta equals to half for all dimension, and considering these results, beta will be 0.5 in 2D as we are getting in the square lattice, and for beta equals to 0.5, and beta is nearly equal to, beta is comparably similar for the simulation case and the analytical case. So a related study is the exit probability, and this exit probability is defined as the probability that the final state corresponds to all upspins starting from x0 fraction of upspin. So as I have talked earlier, the system in one-dimensional Ising system can always reach ground state, and for two-dimensional case also, two-thirds of the cases a system can reach consensus. So depending on the so here we are checking that the probability that configuration will end up, what is the probability the configuration will end up with all spins up starting from a finite number of upspin. So exit probability varies linearly with x for one-dimensional Ising model. For the short range interaction case, exit probability is linear for 1D Ising model, which is with this result is already available. So I have checked here for the mean field case where two neighbors are chosen randomly, and here I also see that the exit probability varies linearly with the initial fraction of upspin, and it obviously it is time it is system size independent. It always shows a linear behavior with x0. But for 2D Ising model, these exit probability shows a non-linear behavior, and as I have shown in the this graph, that the violet one is for smaller system size and the blue one is for the larger system size. As the system size increases, the exit probability becomes steeper and steeper with the system size, and we can conclude that in the thermodynamic limit these will attain a step function like behavior. So to obtain data collapse for different system sizes, we have plotted x minus xc by xc l to the power 1 by nu, where x equals to 0.5, that is the purely disordered state, and 1 by nu, and nu is the scaling exponent, and we have obtained a data collapse which is shown in the inset. This data is for a square lattice. So the in the square lattice, we in the inset we see a data columns for different system sizes, and we try to feed the scale data with a scaling function, that is fy equals to 1 plus tan hyperbolic lambda y by 2, and it fairly it agrees well with the result. And we to investigate the universality of this exponent and the scaling function, we have also conducted a simulation. We have also measured the exit probability in a triangular lattice system, which also shows a similar behavior like square lattice case. The uh, graph becomes steeper as the system size increases, and we
Excuse me, just
yes.
one interruption that 15 minutes is up. You should wrap up as soon as possible.
Okay, sure. So, and for triangular lattices, we have shown the similar results. Here, the scaling exponent is nearly equal to for the square lattice, but the scaling variable is different. That is, the lambda is different, but mu is same. And for mean field case, if we talk about the mean field case, here it was for short range interaction. But if we did simulation for the mean field case, we can see that the scaling exponent is same for z equals to 4 and 6. So it doesn't depend on the number of neighbors in the mean field case, but the lambda is different. That is, the scaling function is different. So now I will talk about the generalized Botan model. For a generalized Botan model, spin free probability is defined as Wi sigma equals to half of 1 minus sigma fi of sigma, where fi of sigma is the fi of sigma is the sum over its nearest neighbor interaction, and we have obtained a similar master equation. And for similar master equation, and here we obtain a consider stability analysis for the solution of the master equation, and we get a I obtained a phase diagram for the generalized Botan model. And for generalized Botan model, this is the yellow region is the paramagnetic phase, and this one is ferromagnetic phase. We obtained a phase transition, but this, as we have used mean field case in this case, so it shows a larger region that is ordered compared to the two-dimensional case. So, so now I make the conclusion that the dynamics is at zero temperature in Ising-like system with up-down symmetry with different coordination number is studied, and mean field approximation always leads to one unstable fixed point, and the stability of the execution function stability of the x equals to 0.5 fixed point for the higher values of z indicate that exit probability should be a step function in the mean field case in thermodynamic limit, which is also true for short range interaction. And in the exit probability, the scaling exponent shows weak dependence on the lattice structure. And but for z equals to 2, the results are independent of the range of the interaction. If we take the mean field case or we take the short range interaction in the lattices, the exit probability always shows a linear behavior in this case.
Thank
Thank
you
you.
for the very interesting talk. There is already questions. The first question is from Tovik. It is just a basic question. Is there any other approach that can be used instead of taking the master equation approach for this work?
What? Can
Uh, is there any other approach? Shovik, can you explain by audio? Unmute yourself.
Yes, actually, I want to know that uh, you are actually treating the Ising model, right? So
Yes.
there are so many different approaches that can be taken to
Yes.
tackle the Ising model for different systems. I am just
Yes.
asking for this particular system, is there any other approach, or is there any specific reason for using this master equation like approach?
No, actually, I have taken the simplest master equation. I have
Yes,
I
yes,
have not taken
that's actually
using
true.
a
That
short
is the
range
simplest.
interaction. Yeah. This is the
Simplest one,
simplest.
yes. And considering the short range interactions, right,
Yeah.
that you have described in the plot.
Can you pardon? Can you please repeat once?
Yes, actually, here you are considering the short range interactions, right? And the
Yes.
simplest approach for this is the master equation approach. So that
Yes.
is used.
Yes.
Okay, thank you.
Okay, thank you. So the next question, rather a query, is from Professor Runav Chakraborty, that he says that I am a bit confused. If you have analytically exact results available, Why are you trying to match that, to verify with numerical simulation? Are you planning for cases where you cannot do analytical work and want to check if your codes are working fine, or I am misunderstanding?
No, actually, I have conducted simulation both on numerical. So the analytical results are available for purely disordered state. Okay. So when the system was purely disordered, that the fraction of upspin is half and fraction of downspin is half in the system. So we have studied the system for a smaller variation from the purely disordered point, and try to see the analytical results of the system with the
Or is it like
Yes, yes.
everyone is facing with that?
Yes,
That, how does
actually,
that behavior work?
I have tried to check that, but for the as the simulation is for mean field case, so the saturation is attained much faster. As I
Yeah.
increase Z, so the saturation is saturation is reached very rapidly. So for I have seen, as I have shown in the picture, so for Z equals to greater than 6 or so, I have tried to check, but as though exponential region is so short that I cannot determine the exponent actually. Then I have to take a larger system or so. Okay, the results are not available for now. So I will try to check that for a larger
Okay, okay.
system sizes.
Okay. Thank you very much for this very interesting talk. So with this session, the last session of oral presentation ends. Uh, I would request everyone to upload their slides on the Slack channel, and so that people can post their questions over there. And also, I would request everyone to fill up the form, the Google form link that is available on the chat box, so that we can send them the participation certificates to all of them. So now you can unshare your screen, stop sharing your screen. So with this, I will hand over the session to Shovik again. Thank you.
Okay, thank you, Samrat, as well as all the speakers. I would like to request the participants to visit our Slack channel for the posters. The speakers are also requested to upload their slides in the Slack channel as well. So finally, we are at the end of our 2-day long conference. On behalf of Team ICCMSP, I would like to thank each and every audience at Google Meet as well as YouTube. And we have a very nice interaction sessions for the plenary talks as well as the oral presentations, and very nice participation all over the crowd, all over the audience. And I am finally handling over the mic to our departmental head, Professor Arunav Chakraborty, to conclude officially and deliver the vote of thanks. So over to you, AC sir, and thank you all.
Thank you, Shovik, Samrat, Moitra, Somodeep, and everybody. Uh, so it has been a wonderful experience for us all, I believe, and I am I am eager to thank sincerely everybody involved, beginning with the authorities of Presidency University, Honorable Vice Chancellor, who has been kind enough to give us approval to hold this conference online and using the Presidency logo, and to do it under the umbrella of Presidency University. And as I told on the very first day, that is yesterday, while inaugurating this event, that it is totally a student-driven activity. We have been trying to do this for a couple of years now, and I am also I thank all the students involved here, Suvik, Shomrat, Moitra, Somodeep, and their friends, okay, whose names may not float up easily here, but they all have been behind this wonderful series of talks and the poster sessions, and the arranging for the links and sending the links to everybody. And no doubt that I am also indebted to Professor Muktish Acharya, who always has stood by me, and jointly we just are trying to put such an adventure as a regular, put in front of you as a regular event, because nothing is actually beyond academics in an academic institution. So I think the students enjoyed the session, and we hope to organize such events in future. With your collaboration, with your cooperation, we can hope that such events will be grand success again. So thank you all. We are now closing closing formally the interaction session and the international conference on condensed matter and statistical physics. Thanks.